Welcome to Tech Talk Thursday, Season 4, Episode 6. As the demand for tighter lines, spaces and hole ratios grows with new applications, Additive Circuit Technologies have made some strategic acquisitions to exploit a new additive plating technology that will enable next generation circuitry. Here to discuss this with me is President and CEO Dave Torp. So my guest today is my old friend and colleague Dave Torp. Dave Torp has been in many different positions throughout the industry. I've known him when he was at Collins Aerospace, Kester, a little bit at IPC, and most recently at Merck. But he has recently joined Additive Circuit Technologies as their president and CEO. Maybe, Dave, you can perhaps tell us a little bit about Additive Circuit Tech and what your plans are there.
Well, thank you, Trevor. It's great to be here, and always a pleasure to talk to you. So from Additive Circuit Technologies, basically they have some proprietary and patented technology that allows for circuits to be created in an additive methodology rather than the traditional subtractive methodology. And if I go back to my IPC days, there are standards on how to create printed circuit boards, and there's a fantastic amount of people and community at the IPC who determines what the best practice is. Okay, so I can go to the IPC 6012 and look up what's the best way to make a printed circuit board. And it all is well and good until you get to about 50 micron lines and spaces, and then after that it all falls apart because obviously best practices are kind of rear view mirror looking activities. Okay, and so you have to figure out how to do something smaller, faster, thinner than what the current state of the industry is, and that's where Additive Circuit Technologies kinds of brings that technology and says, how can we do it differently? How can we get the feature sizes that the industry needs without necessarily compromising the quality, the reliability, and all the what I'll call risk mitigation things that specifically like the military and aerospace guys want, the medical device guys want, and so that's where it kind of comes into play. So we're boldly going into some places that aren't in the standards, and we're working with those subject matter industry experts at our customers. We're working with some of the innovators in the industry. So it's really kind of a power of we standpoint rather than just what Additive Circuit Technologies is doing. We are part of the community that will bring that next generation technology kind of into the mainstream products. And so the technology itself, all by itself, is not necessarily all you need to make that great thing happen. You need the ability to deliver products that embed the technology inside, and that's where the acquisition of Winonix last year and the acquisition of Bench to Bench this year provide that delivery mechanism for the technology to be incorporated. So Winonix is a very capable supplier of rigid circuit cards to the avionics, the aerospace, the military market space. And Bench to Bench is a very renowned supplier in the medical device flexible circuit market. And so both Winonix and Bench to Bench gives that delivery mechanism of a dependable supplier capable of delivering high quality, high reliability product to the customers. And they've been doing that for years and years and years. And now you start to take that additive circuit technology and embed it into those cases where the customer needs that next generation technology in terms of feature feature size lines and spaces for a variety of purposes. Most of the driving force is miniaturization, as you know. Things are getting to the point you can't see them anymore, Trevor. You think it's your eyes, it's not your eyes. Things have gotten smaller. Where graduated bifocals or trifocals or quadfocals or whatever you want to call them.
Yeah, you can hardly see it these days, can you?
You can hardly, the components are looking on the order of a size of a piece of pepper. So you can't tell the difference between a chip capacitor, a chip resistor, and a piece of pepper. Right. And the dies are getting extremely thin. And so you start to take a look at that next generation of technology in the heterogeneous integration. Okay, so it's not just the designer doing the design thing and the chip manufacturer doing the chip thing and the board manufacturer doing their thing.
You got to make it all really together.
Yeah, it's really, you got to start with the end in mind and develop and design and look at those capabilities, look at those enabling technologies from the onset. And you need suppliers to be able to deliver those enabling technologies in a reliable system. And so that's the package that Additive Circuit Technologies is trying to put together for the industry. So as you know, I've made a lot of friends throughout my career, and it's going to take all of them to bring everything over the finish line. So I've reached out to many of my colleagues I've met over the years to get the help. It's really a partnership within the supply chain. So it's not just from the bottom to the top of the supply chain. You need all partners to be able to work in concert with one another to deliver good product on time without too many excuses.
Right. So let's take a closer look at the technology, Dave. I mean, as we stand at the moment, what sort of lines and spaces and aspect ratios are you getting down to?
Well, we're, from a traditional standpoint, we're comfortable with the 25 micron lines and spaces at this point. The pushes with the laser imaging that the capabilities are, we're looking to push down to 15 micron lines and spaces throughout the course of this year. And then in the next year, we're going to get crazy and try to do, something on the order of 4 micron lines and spaces. Wow. Can't promise anything, but that's where what we're defined by is at laser definition. Yep. And how those lines can be laser defined, but that's the only at that point that's the delimiting factor right now. And there's some very good partners we have in the in that space, some equipment partners we have in that space who are helping us out and kind of getting that process dialed in. And in addition, for what I'll call a current state-of-art printed circuit board shop to get the resolutions is one thing on the laser definition, but you also have to be able to laminate it. Yes. Okay. You also have to be able to drill those holes. Okay. Because on a 4 micron line or whatever, it's the hole size becomes challenging, and the plating becomes challenging, and the etching becomes challenging. So there's a whole symphony that needs to be conducted on the manufacturing floor in order to get product generated that's capable product. So that's where we're upgrading. We're making a multi-million-dollar investment into state-of-the-art equipment so that the rest of the process can keep up with the laser-defined features that we can do.
Right. So I mean, how much of this process, I'm guessing, is going to be done in a clean room environment?
Definitely the laser definition, definitely part of the developing process when the chemistry is doing its magic. But beyond that, you can kind of run in a traditional process. So the front end of the process is definitely going to be done. The photo imaging is going to be done in the in the clean room environment. But after that, after you get free of dust and everything, in the wet chemical side of things, the plating side of things is going to be done in a traditional, kind of pulse plating methodology to get the pattern plating, running. So that'll be in a traditional plating operation.
So obviously, additive printing is it's an additive process, but I mean a build-up process, should I say? So, what materials are you using to build it up? Are you actually using, copper and
Yep, using copper, traditional materials, and where you start to see the difference between the additive process and the subtractive process. Traditional subtractive process uses acids to etch the copper away.
Yeah.
And the trouble when the traces get so small, there's a thing called undercutting. So the acid not only etches down, it also etches in. And when you don't have too much to etch, that undercutting, you don't have any bite into the substrate. If you're familiar with the copper foils, they put a little tooth in the back of the foil. When the foil's not big enough to support a tooth, the teeth are very shallow. The teeth are not necessarily. And so you wind up going to a semi-additive process or something of that nature to try to get the adherence or the adhesion you need onto the substrate itself. And that's where the additive technologies differentiate themselves. And that's where our additive circuit technology allows for getting better adhesion, which is a challenge because the current methodology to measure adhesion is to take a piece of tape like a Band-Aid and just rip it off really quick and see how many conductors you have left. And so some of the metrologies we're using as part of the IPC standard test methods are going to have to change a little bit as you start to look at these finer and finer features, because the old what I'll call testing methodologies are just a little bit what I'll call gross for the fineness of features that you're looking at. So but from a differentiation standpoint with respect to the additive circuit technologies and the subtractive process is really the adhesion that you wind up with the conductors that are embedded into the surface of the circuit card.
Okay. Okay, and so and the photo imageable side as well. I believe that's meant to be improved. Yeah.
Absolutely. If you can image it, we can plate it. And we're working with some great people in the industry. There's a lot of subject matter experts, as you know, out there. You interview them on a regular basis, and it's basically just connecting some of the dots within the industry to make sure we have a very robust process that can enable some future designs that currently are kind of I think the designers are waiting for the enabling technology to bring some of those designs across the line.
Right. Now you mentioned heterogeneous integration there. I mean, so are you in your designs of materials for these boards? Are you making sure that they're all very, hyper compatible, suitable, so that you can create these?
Yep. The material selection is critical. From a design standpoint, and if you look at a lot of the high frequency applications, they require specialty materials that have certain dielectric characteristics that allow for the signals to be transmitted at a certain frequency or a certain speed. And so you look at the high frequency component of it using specialty materials, and you start to look at the high speed component of it. If you look at the data that is being generated now in comparison to what it used to be generated. You're going from, the zettabyte territory to the, decades of zettabytes
Right.
being transmitted in the future. And you can see this in, the automotive systems, the vehicle, within the vehicle, you have a large number of electronic sensors that, are giving proximity to the vehicle next to you. And then, future wise, they're looking to, look at, vehicle to vehicle communication. So you're not only communicating, in kind of a within vehicle kind of, projecting outward, you're also looking to communicate between vehicles and such. So the vehicle and the bodies in motion have so much more data that are being transmitted and received and processed. The faster you can do that, and you can see it in your cars. 10 years ago or 12 years ago, the latest and greatest backup cameras. Okay, you put your car in reverse in the backup camera, and you wait a little bit for that image to come up on the screen. It's kind of like waiting for the cathode ray tube to warm up a little bit, and now it's almost instantaneous that you put it in reverse. And so you see the speed at which the data gets transmitted is becoming faster and faster and faster. And you do that by creating the shortest distance between the 2 points. You want to get the plating such that you have the fastest transmission that you can of your data. And you also, on the attenuation side, you're looking for the higher frequencies. And in both cases, this is kind of the enabling technology that allows some of that to happen. But that, so that's where you kind of see that that drive towards more and more and more data is driving the feature sizes and the constructs to become more and more and more complex. And that's what we're trying to help the industry enable. We're just a piece of it. You got the design end of things that need to be in alignment with the manufacturing and the fabricator end of things. So if you look at it, it's really everybody in the supply chain playing well together in enabling the technology.
So are you offering the design services yourself because you're using so many unique materials and things?
Yep. Yeah, for both Winonics and Bench to Bench, that's what we're amping up is our ability to help folks design for excellence and to learn how to use these design features into their products. The trouble is there really is no standards out there for design, and we'll be helping educate customers kind of initially, and then working with the industry trade associations in order to try to take a leadership role in some of those design standards that just haven't been done yet. It's not best practice quite yet. It's more on the leading edge rather than the trailing edge or the best practice edge. And it takes, about 7 years before something goes from, what I'll call state of art to revenue center of gravity, kind of thing. So we expect for the next few years to be working with the communities and getting some design guidelines out there for this technology.
Well, as you mentioned at the beginning of the program, a lot of these standards are really legacy standards. They follow the technology, they don't lead it. So it's obviously something that you'll be looking to incorporate, I'm sure, as you mature this product. A final question. I mean, you talked a little bit about some of the harsh environments you get in automotive. What other harsh environment applications can you use this additive technology in?
The aerospace and military applications have traditionally been very harsh. Whether you're going into outer space or whether you're just doing kind of the ground-based type communication, but you're looking at vibration is a function of how many G's or how many RMS can you take on the vibration piece of it, and then you start to also look at the temperature extremes, the minus 55 to plus 125, or the minus 65 to plus 150. So the temperature extremes start to become a play, and so you start to take a look at smaller, lighter, faster type modules. The overall mechanical structures have changed a little bit. The weight reduction helps in some respects, but you also have to make sure that things are capable of withstanding the gunfire blast or the missile type accelerations, which are extreme. So we believe with respect to the technology, we have a competitive advantage with respect to the amount of force that these circuits can withstand, and so we're well positioned within those harsh environment market segments.
Okay, great. So, final question. I mean, when can we expect to see the first circuits rolling off the system?
Yeah, throughout the course of this year, we're making a multi-million-dollar investment into upgrading all the capabilities within Winonix and bench to bench to showcase the technology. We expect in Q1 2022 to have the technology embedded and functional in several what I'll call higher level new product introductions and prototypes that'll be coming out to the market. So primarily for the aerospace, avionics, and military space initially, we're migrating into the automotive space as a next level kind of process. And for bench to bench, it's going to be in the medical devices, giving them the ability to get the miniaturization and the sizing that they desire. So it's not as harsh of an environment as the military, but it's just as rigorous with respect to the reliability and the mean time between failures. They don't want any failures in their diagnostic equipment. They like it to work right the first time, every time the same way. So
absolutely. Well, Dave, it's great to see you raising the bar as always.
Yep. Well, we stealing from my friends at Merck, we aim to make great things happen. So part of the fun of it is to do something that hasn't been done before, and do it in a way that realizes the technology in a very pragmatic, very practical. And so for the flex circuit market and the rigid board market, I think we'll be able to make some great things happen and give some of the designers out there some new tools to work with so they can perpetuate that making great things happen. So
Right. Well, it sounds like an exciting journey you're on, and we wish you every success with it. And I want to thank you for coming in and telling us about it today.
Thank you, Trevor. It's a pleasure, and you stay well, okay?
Okay, thank you. You too.
Take care.
eSmart Factory 2021 is an international hybrid event.
Share the room, or the internet, with some of the smartest electronics manufacturing engineers.
Learn directly from those who are implementing smart factory strategies or creating the software systems and standards of today and tomorrow to meet the rising industry challenge for reduced risk, reduced scrap, and reduced machine downtime, providing you with a competitive edge to improve your reliability, your yield, and your profit. Of course, we'd rather see you in person at this year's 2-day hybrid event, but whether you are located in San Francisco or Shenzhen, eSmart Factory 2021 is the conference where you'll learn all there is to know about intelligent manufacturing.